Bismillahirrahmanirrahim. Assalamu alaikum dear students. Today we are going to continue with our sheet 8, and last time I solved with you the problem from 1 till 6. Okay. Today we are going to do the seventh problem, which is different than what we did previously. This problem involves the Amdahl's law. So Amdahl's law is used to find the maximum expected improvement to an overall system whenever only a part of system is improved here. Okay, so we have a straightforward formula. We are going to just substitute the value, and we are going to find out that by doing this enhancement or this change to a system, we will get the maximum improvement to the overall system here. So the formula, let me write the formula here. I'm writing the general formula. According to the number of terms, we can make the changes here accordingly. So basically what we have S, maybe write the formula here better. The formula is S u of 0 will be equal to 1 divided by 1 minus delta 1, you can break in bracket here, plus delta 2. If you don't bring the bracket, it means 1 minus delta 1 minus delta 2 and so on. Okay, so it doesn't matter, it's up to you. It's only a mathematics here up till delta n. So this whole term plus delta 1 plus delta 2 plus up till delta n divided by SU of delta 1 plus SU of delta 2 up till SU of delta n here. So this is a general formula to calculate the overall improvement in the performance using the Amdahl's law here. Okay. So let us start our question here. The question is, he said that, for example, 3 enhancements are being made here. Okay, so he said that we have basically 3 enhancement. So with the following speeds up are proposed for a new machine here. So basically this is the speed up of certain enhancement A, speed up of certain enhancement B, and the speed up of certain enhancement C here. So according to the question, basically he said that the 3 different enhancements are, let me write it. Let's suppose the 3 enhancement according to the question are A, B, and C. Okay, it can be anything basically. So he's just writing in terms of general terms here. So 3 different enhancements are A, B, and C here. So the speed up of enhancement A is 30. So I can say that this is SU of delta 1 term here. Okay, so I can say it's U of delta A here, which is 30. Basically, I'm talking about these terms here. Okay, so then we have similarly we can have SU of delta B, which is basically 20 here, and we have SU of delta C here, which is 15 here. Okay, now he said that assume that for certain program a fraction of use is 25% here. So basically he said that for enhancement here, basically what he's saying, he's applying this enhancement A on certain program for only 25% of the time here. So it means that this is basically the fraction of time for which we are applying the enhancement here. So it means these are your delta values here. So since this is 25% here, let's say this is, for example, delta of A enhancement speed, the fraction of time for A will be 25%, which is basically 25 by 100, so 0.25 here. Similarly, the time fraction for the B will be 30%, which will be 30 divided by 100, which is 0.3, and for enhancement C it is 45%, which is 0.45 here. Okay, so basically this information is provided to us. Now he said that if one enhancement can be implemented, the first question is if one enhancement can be implemented here. So what is the maximum uh, or which of, if one enhancement can be implemented, which one we can select to get the maximum speed up here. So it means that we are going to look for the enhancement out of A, B, and C, or which one will provide the maximum speed up here. So for that, basically, we need to calculate the the overall speed up of a system using this formula for A, B, and C individually here. So in this case, for example, what he mean basically, if he apply enhancement A, how much overall speed up will he will gain? If he say enhancement B, how much overall speed he will get? Or if he do the enhancement C, how much overall improvement or speed in the system he is going to get here? So accordingly, the one which is going to give you the higher value can be selected, which is the one which is giving you the maximum speed up when implemented in the system here. So let's suppose for one enhancement here, okay. Enhancement means a modification or change in the system here. So if one enhancement can be done at one time here. So what will be the overall speed up due to enhancement A here? So simple. We have only three terms here. So from the general formula, I'm going to go till delta 3 only here. So it will be, let me just, since I'm talking about one enhancement right now, so I will be only going till delta 1 only. So it will be 1 divided by 1 minus delta A only plus delta A divided by SU of delta A here. Clear? Which will be basically equal to 1. All the values are provided to you. Just substitute the value. 1 divided by 1 minus delta A is 0.25 plus 0.25 divided by SU of delta A is 30. Which is basically equal to 1.3186 here. Similarly, we can have SU of B. The formula will be 1 divided by, I'm not writing the formula again, but I'm just writing it verbally, saying it. 1 divided by 1 minus delta B plus delta B divided by SU delta B here. So just substitute the value, it will be 1 divided by 1 minus delta B is 0.3 plus 0.3 divided by SU of delta B will be 20 here, which is basically equal to 1.3986 here. Okay. Similarly, we will be doing SU of C here. For C, it will be 1 divided by 1 minus, for C, it will be delta C 0.45 plus 0.45 divided by SU of delta C is 15 here, which is basically equal to 1.7241 here. Now, which value is the maximum here? Obviously, the last value which we calculated is the maximum value here. So it means that the enhancement C can be adopted to get the maximum speed up overall, to improve the overall speed up of the system. So it means enhancement. Well, let me write it down and I can do the question on this side here. So enhancement C can be selected what he said so enhancement C can be chosen to speed up the system here. Okay, brother. So this is how we are going to calculate the first part here. So now let us continue here. We say that if we apply the two enhancement at the same time here, so what we are going to choose here. Okay. So let's suppose I'm just doing it here. If we apply two enhancements, so what is the possibility here? Either it can be enhancement A or B, or it can be B and C, or it can be A and C here. So this is the three possibilities we get here if we apply two enhancement at the same time here. Okay, so let's suppose, so we will be calculating for each particular scenario here. Okay, so we can say that um, if what will be the overall speed up if we apply the enhancement A, B and together here. So it will be 1 divided by 1 minus delta A, sorry, minus delta B. Okay, if you say, you can say 1 minus, and you can bring them in the bracket here. Okay, so up to you. It's up to you how you feel comfortable in and solving the mathematical terms here. Plus delta A plus delta B divided by SU of delta A plus SU of delta B. Okay, so all the values are available. Just substitute the values here. So it will be 1 divided by 1 minus delta A is 0.25 minus delta B is 0.3 here plus 0.25 plus 0.3 divided by SU of delta is 30 plus 20 here. So just calculate this all terms here. The value which I end up with is 2.169 here. Okay. So this is what we are going to do here. Similarly, we can find it for B and C here. So SU of B and C will be equal to 1 divided by, I'm not writing the formula directly, I'm just writing the values here. 1 minus delta B is 0.3, delta C is 0.45 here, plus SU of delta B, SU of, sorry, the same thing, delta B will be 0.3 plus 0.45 divided by SU of delta B will be 20 plus 15 here, which is equal to 3.68 here. Okay, we do the same thing to find the SU of A and C here. So the overall speed of SU of A and C will be equal to 1 divided by 1 minus A is basically equal to 0.25 minus C is 0.45 here plus 0.25 plus 0.45 here divided by 30 plus 15 here. Okay, so just making a calculation here and you end up with 3.168 here. Now, which one of these three we are going to choose here? So we will go with the higher values. Obviously, A and B giving me 2.169, which is the small value than the remaining two, and 3.68 is the larger value among R here. So it means we are going to choose the enhancement B and C to speed up the overall system here. Okay, so choose the enhancement B and C to maximize the maximize maximize the overall speed of the system. Yes. Okay, so it's a straightforward formula. We need to select the one which gives us the maximum value, and we choose the one to maximize the overall speed of the system here. Okay, now let us start with our new sheet, which is sheet 9, and it's about programming the basic computers here. Okay, so we start with the first question. I just change slightly the question, make a table, because this is what we are going to fill here. The question is, first of all, the following program is stored in the memory unit of a basic computer. So this program is already stored in a computer here, memory you can say. Let me say that this is the memory here. So this is already stored in the memory of a computer system here. Okay, now he said that this is the location, like these are all the locations here, means at this particular location in the memory this particular instruction is stored here. Okay, now he said that show the content of AC, PC and I are here. So we need to show the content of AC. We need to show the content of AC here. We need to show the content of PC, and we need to show the content of IR here whenever basically after the end of each instruction is used. So he said that we need to fill the table, like we need to fill the values of AC, PC and IR when we finish with the execution of these instructions here. Okay, so first of all, what we have, if you observe here, like in all the location, like these are basically all instructions here. But if you notice here, this 016017, this does not represent any instruction here. This is the instruction list you have studied so far. These instructions are not available here. Okay, so it means that these are basically my operand which are stored at this particular location in the memory here, and I will be using them for calculation purpose here. Okay, so it's more or less what we did in the sheet 7, I guess. Okay, so let us start here. First of all, when we start executing a program, we know that the program counter is incremented by 1 by default here, okay, initially. Unless if it is a branch instruction, the value will be changed according to where we want to jump or where we want to branch here. So when we start with executing the instruction at 010, so next time the program counter should execute the instruction at 011, means it should be incremented by 1 here. So the program counter will be incremented by 1 directly here. Okay, next thing is, what is the instruction doing here? It is basically clear accumulator here. So it means that the value in my accumulator will be cleared here, and it will become 0 0 0 0 here. Okay, like this is a 16-bit register here. Next thing is, he said that what will be the value in the instruction register. So the value in the instruction register, we are going to use this table here to write the values in the instruction register here. So the command is CLA. So for CLA, the value is 7800 here. So we will be writing 7800 from the table here, mean this value here. Okay. Now we go back again. Next time what we will do, the program which is going to be executed will be 011. So at 011, it is an add instruction. So we need to add the content which is present at 016 along with the content of the accumulator here. So basically, normally what you have, your accumulator, the add instruction I'm telling, okay, it's like accumulator plus DR here. So in the DR, the value which is stored at 016 will be loaded in DR here. Okay, so basically this value which is at 016 is C1A5. The content in accumulator is 0000 here. So obviously 0 plus anything will be the same value here. So we are going to have the same value here. Okay, so it's not like a big science here. So it means that my accumulator value after executing this one will become C1A5 here, and the program, sorry, the content in my program counter will be, obviously it will be incremented by 1, so it will become 012 here, and the value in my instruction register will be, the add is basically, since at 016 I had my operand here, so it means the instruction was and direct instruction here. So we need to look for these values here in this question. I think so all of them are direct here. So for add, it is 1 here, so it means it will be 1 value, sorry, if you remember, it will be 1 plus the value which I will have in my address register here, which we are not recording here. So obviously the address register will be the value which is 016, because we went to this value to store or to load the program in DR here. So it means that it will be 016 here. Clear, like what we did previously in the sheet 7 here. But we need to write the initial value in the address register here. Okay. The next thing is, the instruction which we are going to execute will be at 012 here. So it means we will go to the at 012. So at 012, what we have branch 014 here. So first of all, the program counter is incremented by 1, which will become 013 here. But since this is a branch instruction, means we need to jump to this location. So the program counter will be 014 here. and obviously it's only jumping to certain location. There is no change in the content of accumulator here, so the previous content of accumulator will continue as it is, and for branch here it is basically 4 here, so it will be 4, and the value in my address register which will be 01014 here. 4014 will be my instruction here. The next one is we need to execute the instruction at 014. So we will come to 014 here. Okay, we will come to this instruction now here. So at 014, basically, first of all, this is an AND instruction here. So in the AND instruction, obviously the program counter will be incremented by 1. So it will become 015 here. And it should perform the AND operation here. So the AND operation it will perform will be between the value of the accumulator along with the value which is present at 017 here, which is this value here. Okay, so basically what we have in my accumulator, let me write here, in my accumulator right now, the value I have is C1A5 and I need to perform the AND with 93C6, 93C6, and you need to store the value here. So what we will be doing here, we will be converting it into the binary here. Okay, this is the hexadecimal value. So C will be equal to 1100 here. This is 0001 here. Then this will be 1010 here, means 10. 1100 is 12 basically. Okay, 0, so 0, 0, 5, so 10 here. 0101 here. Similarly, 93C6 will be equal to, so 1001 is 9, 3 will be 0011 here, C will be 12, 1100 here, and 6 will be 0110 here. Okay, so what we will be doing here, we will be performing the AND operation between them here. So 10 is, for AND what happened? The output is 1 when all the inputs are 1. Any single 0 make it 0 here. So 0, 0, this is 1. This is 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0. This is 0, 0, 0, and this is 1 here. So when we converted back, so it will become 8, this value. This is 1. This is again 8 here, and this is 4 here, I guess here. Okay, so basically in my accumulator, it will be 8, 1, 8, 4 here. So this is the value which we are going to have in our accumulator here. What will be the value in the instruction register? So in the instruction register, obviously this is AND operation, so this will be 0 here. So I will be having 0, and the value in my address register is 017, so it is 017 here. Okay. So the next instruction we are going to perform will be 015 here. So we will go to 015 here, which is again a branch instruction here. So branch means the value of PC will be pointing to the branch address here, which is 013 here, and obviously no change in the accumulator value here, and the instruction register value will be branch is 4, so 4, and the address register value is 013 here. Next instruction which we are going to execute will be the value at 013 here. So we will go to 013, which is basically a halt value. Halt mean we need to halt the computer, we need to stop the program here. Okay, so what we will have here, see if this is halt here, so no change in the accumulator here. Program counter as usual will be incremented by 1 here, and the instruction register will point to this value which is 7001 here. Okay, so this is how we are going to fill the value here. Here this small change here, basically this will be halt is like we are at 013, so it will be incremented to make it 014 here. Okay, small modification, sorry, because it is incremented by 1 normally. Okay, let us start with the question number 3 here. Question number 2 and 4 I will do next time, which is both related to the programming here. Okay, so the question number 3. Okay, he said that a line of code in an assembly language program is as follow here. So he has given a line of code, and a line of code is basically, we said that it is stored in 2 consecutive memory location where the 2 characters are stored in each location here. Okay, so since one word capacity is 16-bit here, so we can store two memory words which are of 8-bit each here. Next thing, he said that we need to show that, like for example, this is DEC decimal space minus 35 here. So this command, which is a line of code, it should be like followed by an enter sign here, which we will call it as the carriage return here. Okay, like normally when you write a code, you press an enter, and carriage return means the cursor comes to the start of a next line here. So this is like the enter here. Okay, so show that 4 memory words are required to store the line of code and get their binary content here. So basically we are interested in writing that what are the content in the 4 memory words here, because he said that we need 4 memory words here to store this particular command here, and we need to write the binary content here. So what we will be having here, we can have a memory word here. In fact, memory word number, you can say which number. Okay, next one is which characters we are storing here. The next will be the hexadecimal value, which I will be writing here, and I will leave the binary for you. Basically you can write the binary value yourself here. Okay, so in the memory word 1 here, what we will do, we are going to store the first two characters here, which will be D and E here. Okay, so we can store in the memory word 1 the character D. If you write E, so I'm just not writing anything here, so D and E here. What is the hexadecimal code for this one? So we have an XT code here. Okay, the table here. For D this is 044, and for E basically is 45 here. So from here I'm going to write the 44 and 45 here. Okay, if you convert in the binary, let me do the first one. Obviously each character in the hexadecimal will be represented in the 4-bit binary here. So 4 means 0 1 0 0, again 0 1 0 0 here. This is the 4 here. Then 0 1 0 0 and 0 1 0 1 here. Simple. Okay, so I'm not writing it for the remaining digits here. You can write it yourself here. In the next memory character, what we will have in the next one, obviously we will have C along with the space here. So it will be basically C, and for space I'm just writing a dash here. Okay, or in fact let me write a space here so you don't confuse here. Okay, like when you press a space with a space bar, this is what you are going to get here. So obviously for C from the table it is 43, and space from the table is 20 here. Okay, you can convert it in the binary yourself. The third one will be we are going to write minus 3 here, or dash 3 here. Okay, so minus is 2D here if I'm not wrong, and 3 will be basically 3 here. Similarly in the 4 memory word here, it is going to be 5 followed by the enter, which is the carriage return here, CR here. Okay, like it's like carriage return here. So obviously for 5 the code is 35 here, and carriage return is 0D here. Okay, so this is what are the content in our hexadecimal. We use this ASCII table to write it. You can convert them into the binary here, straightforward here. Okay, the second one which we have here is say that show that one memory word will store the binary translated code here, and we need to give the binary content here. Okay, so he said that if we are not using the line of code, we can just use one memory word to store the binary translated value here. Okay, so what it means that the binary translated value will be, for example, right now it means that let me use this one. Okay, it is decimal minus 35, so it means he wants to store a value which is minus 35 in decimal in a memory. Okay, so instead of doing this line of code, writing all the instruction here, we can just only store directly the value minus 35 here. So minus 35, we need to first know what is 35, then we can find the 2's complement of it to make it minus 35 here. So let's suppose the 35, since it is a decimal value here, I'm talking about the part B here. Okay, it will be basically in 16-bit, what it will be 35 means 35. Okay, let me just do 1 2 4 8 16 32 here. Okay, this is like then 64 and so on, if you remember here. 35 in the binary, you can use the table here also, okay, convert it. I'm not using it like doing this one. 35 means it will be 32 plus 2 plus 1 here, and the remaining will be 0 here. Okay, so basically what we have, minus 35 in this is 30, sorry, this is 35, and since we are talking about the 16 bits here, so I need to write remaining zeros to make a 16 bits here. So it's like 4, then 4 here, then it will be 1 0 3 4, so it should be 16 bits here. 4 4 8 9 10 11 12 13 14 15. So these are 16 bits here, okay, in the binary here. Simple. This is just only for my help here, so don't confuse here. Now we are not interested in finding writing the value of 35 here, rather we are interested in storing minus 35 here. So minus 35 means we will be using the 2's complement here. We will be using the 2's complement of this value here, 35 here. Okay, so the 2's complement, I'm just doing it directly here. If you don't like it, use whatever value you know here. Okay, I'm not repeating it because we repeated many times here in this course. So it means it will be 1, then we will flip each bit 0, then it will be 1 1, then 1 0, then 1 1, then 1 1 1 1 1 1 1 1 here. So 1 2 3 4 5 6 7 8. Okay, so this is the binary translated value of minus 35 here. Okay, so since he only needed the binary content, so this is the binary content. But for example, if he asks for the hexadecimal content, just convert it in the hexadecimal. So make a group of 4 4 here, so it will be like f, and this will be like 12 plus 1 13. So it means it will be d here, and this will be d here. This will be in the hexadecimal if it is asked in the question here. Okay, so this was all about today. The question number 2 and 4, I'm going to do it next time, inshallah, which involve the programming here. Thank you. Assalamu alaikum.